made a transition during your talk that the next presentation will be on the L4 mission. So thank you again, Carol, and we welcome the next speaker.
Thank you.
So I guess Joern, or I hope Joern is online.
Yes, I am actually online.
Okay, very good.
Interest.
So we will put your presentation. Let me,
yeah, you should see it now.
Okay, so I can move the slide, and so you just tell me next slide, and I will proceed.
Okay.
Okay, so
okay, that's even.
Joern Helbert, who is our section head of the Solar System mission, and is also following the L4 mission, and he will give us the overview of this project. Thank you, Joern.
Yeah, thank you very much. First of all, my apologies for not being there, but I actually have a very, very good excuse because I'm actually sitting here at ESTEC together with our L4 expert team and our L4 payload team, and we're actually working actively right now on planning this new mission. So if we go to the next slide. So as Carol said, our program has a long-term component, and that is the Voyage 2050 program. And as part of this Voyage 2050 program, the first mission identified was a mission going to the moons of the giant planet. If we go to the next slide. And our expert committee actually said what should be the goals for such a mission. And this is really building on what we have learned from Cassini and what we learned about the outer solar system, and actually going out and exploring the habitability of an ocean world, and actually going there and trying to search for the signs of life on a body in the outer solar system and on one of the icy moons, and make this connection between the interior and the surface environment. And as you know, I mean, nowadays, there used to be that oceans on icy world was something rare and maybe one or two. Nowadays, there seem to be oceans on basically every ocean world we're looking at.
Yes, Joern, we are just doing a small technical check. So wait.
I see.
Still checking, Joern.
I'm very patient. I have to be. This mission is going to take decades, so a few minutes acceptable.
Looks good in principle. Okay, I think. Well, yeah,
okay, perfect.
Yeah, thank you.
Yeah, you can actually go directly to the next slide. Because, as I said, the theme of is the moons of the giant planets. Now, there are a lot of moons. And so we actually had an expert committee coming in and assessing the large variety of moons that we have to actually tell us which of the moons should be our priority. And as you see here, there are the very big questions: habitability, interactions of interior, habitability, interaction with the internal environment, and the periodic chemistry and biosignatures as the big overarching questions. And then we're looking at 4 moons in detail. Europa, Ganymede, Enceladus, and Titan, both in terms of the relevance for the scientific questions, as well as looking at what are actually missions that are selected will already do. And if you look at this matrix, you see that Enceladus is really jumping out at you because it's highly relevant to all these questions. And there are no planned missions right now. So this is something where Europe can really take a leadership role and do a very unique and new mission. And you see, of course, I heard the end of Zivi's talk that Titan was a kind of close second. But with Dragonfly already addressing a lot of those questions, that actually took us to Enceladus as the main target. If you go to the next one. So now we're going to the Saturn system. If you go to the Saturn system and you go to Enceladus, you of course don't want to look only at Enceladus. There are a lot of other moons in there. And so part of this is of course planning also how we can actually explore Enceladus in detail, but also put Enceladus in the context of the ocean worlds in the Saturnian system, which is Titan, there is Mimas, a potentially undiscovered ocean world, and all the other very diverse moons that we actually try to cover during the moon tour that will be part of the design of the mission. If you go to the next slide. And of course, all this builds on Cassini and the discovery of the plumes. I can just click one more thing, there's just text coming in. This is an example of actually sending a mission to a body not knowing what you're going to see, because there was some earlier mentioning of a connection between the E-ring and Enceladus, but the plume in itself was a surprise, and I don't have to tell you how absolutely fascinating the discovery is and how Cassini told us a lot about this, but with a spacecraft that was actually not designed really to study the plumes. And the part that for me is really fascinating about this is that with the plume of Enceladus, this is our unique chance to actually directly investigate the water of an subsurface ocean. While in other words, you can do it indirectly. Here, the plumes actually bring the material and the water from the ocean out for us to study directly. If you go to the next one. And so basically what we learned from Cassini, just summarized in the two very, very broad pictures, is yes, we have liquid water. Yes, there are sources of energies. Yes, there are basically all the fundamental elements. So there is a potential for habitability. And we know that there is a relatively thin ice shell, just 5 kilometers. We have the plume that actually very, very likely connects the ocean to the environment through these cracks. And so basically, we are ready now to do the next step and to actually look what would be the steps needed to actually search for a life on Enceladus. And if you go to the next one. And here we are building on the rich heritage of Cassini as well as on our experience with JUICE, and really trying to develop a smarter, smaller payload that can answer the next big questions that are coming after the Cassini mission. If we go to the next one. And so again, talking to our expert committee during our assessment, an orbiter is, of course, necessary, but it's not sufficient. The next mission after Cassini and after JUICE has to include a lander. We actually have to get on the surface of Enceladus. We have to get as close as we dare to the tiger stripes and have an lander operating on the surface for 2 to 4 weeks, searching directly for a signature of biosignatures, both in the plume, but also on the material on the surface, and as well go tours through the Saturnian system to put Enceladus in the context of the other moons. And of course, do all this in a constraint that we have for all missions of power, of mass. And this is especially true for a lander sitting on the surface. And so this means there's a lot of investment and a lot of technology preparation, development, and maturation necessary that we're starting right now. If you go to the next slide, Carol already shown the slide, so let me just take you through this. So this is the current mission design that we're working with. So it's a dual launcher mission. We are launching with 2 rockets. We are assemble the actual spacecraft in orbit. We have a kick stage that will take us out of orbit, a chemical solar electric propulsion that will take us to the Saturnian system. Once we arrive in the Saturnian system, we will separate from our solar propulsion system. Then we start a moon tour, and you're seeing we are doing the tour of all the big hits in the Plutonian system: Titan, Rhea, Dionys, Tethys, Mimas, and Enceladus. So already during the moon tour, we will pass Enceladus. We do our first sampling of the plumes. Then we're actually going to go into an orbit around Enceladus. We're doing an extensive mapping phase, both to study Enceladus, but more importantly, to pick our landing site. And then personally, and I might be biased there, the most exciting phase of the mission starting, we actually separate our lander and we're descending to the South Pole region of Enceladus, sampling the surface directly, and then doing our astrobiology and our search for biosignatures and for life signatures on the surface of Enceladus. We go to the next slide. Now, if you think this all looks extremely ambitious and very, very complicated, true. It is very ambitious, it's very, very complicated, but it's doable. And this is something that we have been studying with 2 industry contracts in parallel. We gave them this baseline. They actually went and looked in detail in all part of the mission, and they came this summer both back with the same statement: yes, this mission is technically feasible. So we have a robust baseline now on which we can now go in a more detailed study, and that's part why I'm not with you, but actually sitting here and discussing with the engineering and science team, because now we really need to start the preparation and the technology development that are needed so that we can actually adopt the mission in 2034. And I just focus on one element and one of the most thrilling elements of the mission, the landing. Go to the next slide. The big question, of course, is how and where do we land? And as you can see, we're basing here a lot on Cassini, actually giving us the context, giving us the rough area. We know there is snowfall plume material actually going down on the surface of Enceladus. So we have a surface that is partly dominated by rocks and boulders. We see in the Cassini images, but that also will have this snowy, fluffy component, and which means we need to do a very precise landing. The goal here is to, with the landing system, have a landing ellipse in the range of 50 to 20 kilometers, then going to a 1 kilometer landing ellipse, and then having hazard avoidance for the final guidance to actually land on the surface. And all this, again, I don't have to tell you this, given the distance, all this, of course, has to happen autonomously. There will be no intervention from Earth possible. This has to be done with autonomous landing systems in a very harsh and very uncertain environment. If you go to the next slide. So there will be a lot of unique challenges that are different from the challenges that we have for Moon and Mars, because we're basically landing in a snow ice environment, and we have currently only remote sensing data that in best cases about 4 meters, in most cases much less than that. And that's why it's very important for us to have this reconnaissance phase at the beginning of the mission, as well as doing a lot of technology development and early maturation. And to just give you one idea of what we're playing around with here while we have the team meeting. If we go to the next slide, actually what, this might be how landing on Enceladus might look like. So you see here a dummy model of our lander with the astrobiology payload on it, and a snow analog that actually is not too far away from what we're expecting. And so we're basically needing to balance various risks here, avoiding surface contamination, avoiding that our lander actually sinks in, and having good access to the surface material. And if you go to the next slide, which takes me to the time scale. So on the big picture, we actually, on the top line, you see the first paper in the E-rings were about in 1980. Cassini discovered the plumes in 2005, so that's about 25 years. Now, 20 years later, we done our first industrial study. We know there is a mission concept that is feasible. now we have about another 20 years to actually launch a mission, and then it will be about 15 years to arrive and land on Enceladus. And as you know, given the illumination conditions, we basically need to wait until past 2055 to have the South Pole permanently illuminated. That looks like a long time scale and it looks like far away, but those of us involved in mission development know that 20 years are basically nothing. If you look in the middle line, that is, no, actually go back, please. If you look in the middle line, this is basically blowing up this timeline a bit more and showing basically where we are right now. So we are in 2025. As Carol said, we will have the ministerial conference at the end of the year. We're presenting the mission. And then we're going in the mission definition phase. And this is really critical for this mission. By adoption, we need to make sure that we have all the technologies that we need, both for the landing as well as for the live detection, matured to a level that we can adopt the mission in 2034. And suddenly we only have 8 years left to do this. So suddenly those long timeline becomes 8 years in which we need to do the full maturation. Then we have another about 7 years to get to the launch pad in 2042. And then we're off on our long travel to Saturn and finally to the landings on Enceladus. So you see that's why it's very, very important to start now doing all the development, start now really going into the details to make sure that we actually do this landing in 2058. And then at the very bottom, you see the time-lapse emission. So we have that rendezvous phase in Earth orbit. We have about 10 years of interplanetary transfer. And then we have the first phase where we do Enceladus and Titan. We do Titan gravity assist. We do our first Enceladus flyby. Then we do our moon tour, about 3 years. 1 month reconnaissance phase at Enceladus once we got in orbit. 1 month Sessa operation, and then the disposal of the orbiter in a graveyard orbit that is stable for more than 1,000 years. Go to the next slide. And so what we're doing right now in these days here, and before giving this talk, I was literally running up from our meeting room where we had very heated discussions to actually make sure we get our science traceability metrics properly set up in a way that then we can actually look at payload concepts, at technology development, and the goal here is to have a strawman payload before the end of 2026. So again, we are really pushing on the time to make sure everything is ready as soon as possible. If you go to the next slide, which is also my final slide. So as I said, the theme here for L4 is the moons of the giant planets. If you just click again. If you can just, yeah. So we are now in the phase where we're actually refining the science traceability metrics, really focusing with Enceladus as a target for the L4 mission. We're developing a strawman payload, but very importantly, we're developing also the technology maturation or development that are needed and try to kick them off as early as possible. L4 is a highly ambitious ESA mission. It's the first mission that we're really leading in the outer solar system. We think we are ready. We think this is something that can be done. Industry think it's something that can be done, but it requires significant investment early on to ensure that we actually have a very successful mission. Thank you very much.
Thank you, Joern. So I look for questions in the room. Okay, so first question for you.
I'm reminded that when the Cassini-Huygens mission was put together, it was 1.3 billion NASA and 700 million Huygens ESA. And by the time it was finished, it ended up at 3.5 billion, if I remember correctly. So did you have any estimates of what such a complex mission as the one you described for Enceladus would cost?
Well, that is part of, I mean, typically an L-class mission is about 2 two yearly budgets of the ESA science budget, so that's about 1.5 billion. And we are now in the phase where we're actually, with the Strawman payload, going to do a detailed cost assessment to see where we exactly land in the context of that costing.
There was a question. Okay. So another question, Joern. Wait 10 seconds.
Yes, so my question is quite simple regarding the lifetime and the instrument payload. Going so far away, where are we on the European RTG, and can we expect RTG on board such a mission in 20 years?
The baseline for the mission currently is solar powered. I mean, the lander is battery powered and the orbiter is solar powered. And that was one of the questions that we put to industry. Is this durable on solar power alone? And how much would we gain from RTGs? And it actually turns out when the industry came back, as they said, yes, it's doable on solar power. And RTGs would actually not help as much as we were thinking they would help. And so that's why currently we're baselining solar power for this mission. And it's about a 180 square meter solar array taking us to the Saturn system, which is huge, but not unheard of huge.
And Joern, they were talking about fuel cells at some point?
Well, that is part of the trade we're doing right now for the lander. And this is interesting because that is we always talk about spin-off from space and exploration to everyday life. Currently, for the batteries, we actually see the opposite, because for electric mobility, the development of batteries has really progressed massively over the last years. And so now we are actually suddenly see there are battery cells available that would work for us with a very, very high energy density if they were not available a number of years ago. Fuel cells, again, coming out of electric mobility is another thing to look at. And so again, that's part of the trades that are being done over the next months to see what would be the best energy source for the lander. But again, currently looking at modern battery technology, it looks like that the 2 to 4 weeks lifetime on the surface actually is not an issue at all from the power point of view. There are other issues, but the power point of view actually is not a constraining factor.
Okay, thank you. Maybe the last question from Jan-Erik.
I have heard there is not too much mass for payload and that you are trying to do miniaturization. So how are you going to involve the European planetary payload communities which have the experience in that area?
That's actually a super good question, because what we have here now is one hand is the expert team and the other one is the payload working group, which is a cross-section of people in the European communities that apply to actually work on the payload working group. And they're looking in what is available right now, but they're also looking into what need to be developed, what need to be miniaturized. And so you will see there will be calls coming out, and I would very strongly encourage you to apply for that, for the development and maturation of miniaturization technologies for various payload elements.
Okay, thank you, Joern, again.
Thank you.